Okay, so now we have to do a review of Chapter 15, which is our Introduction to Equilibrium. So the reason why we do rates first is because the equilibrium value is related to the rates. But the difference here is that this is the first time that we acknowledge that, wait a second, these reactions don't just go forward, they also go backwards too. And since the reactions go forward and back, that there's no way that we're ever going to complete either one. Meaning that there's never going to be a time where all the reactants have been turned into products or all the products have been turned back into reactants. There are always going to be some of both on each side of the equation or left in that container, but only if the container is sealed. If you allow the container to be opened and you're producing a gas that leaves, then you can go to completion. And that's why a lot of times we don't talk about equilibrium in reactions, because we do it in an open container. It releases a gas, like baking soda and vinegar releases carbon dioxide gas, and the gas goes away. So you can't really establish an equilibrium there because the carbon dioxide has left the reaction chamber and therefore can't re-react to go backwards. But the idea of equilibrium first is that the reaction goes back and forth. So a common equilibrium thing that they like to use is this reaction where you have the N2O4 gas turning into nitrogen dioxide. And the nitrogen dioxide is a brownish gas and the N2O4 is a clear gas. So you can see that visually as you're having the equilibrium go back and forth, you can see the change occurring. So the point of this with the double arrow is that we're going in both directions, right? So there's a certain rate for the forward reaction to happen, right? The rate of N2O4 reacting is going to have a value which is going to be equal to the K of N2O4. And then there's a certain rate of the NO2 reacting, which is going to be equal to the K. So we're going to call the N2O4 the K forward. We're going to call this the K reverse of the NO2, and we're going to say squared. So when we get to equilibrium, everything becomes elementary reactions. So the coefficients in the stoichiometry and the exponents in the rate laws are not necessarily going to be the same when you're dealing with determining what the rate law is. But the minute they say reaction reaches equilibrium, what's the expression? Now you can use those coefficients from the balanced equation in your equilibrium expression, because you're expecting now that any variations from the rate laws are not going to be accounted for here, right? Obviously, in real life, you have to figure out what the real forward rate law is, the real reverse rate law is, and plug those numbers in with the correct superscript values. But when we're dealing with equilibrium in this course, we're going with elementary reactions, meaning that the coefficients match the superscripts or the exponents in the rate laws. All right, so we have a K forward, K reverse. The thing that we now know, though, is that these two things are equal to each other, right? Because when we reach equilibrium, it's the point at which the forward rate and the reverse rate are equal, right? That's the whole significance, is that there's a point that that happens. So that means the Kf of the N2O4 is equal to the Kr of the NO2 squared. And so if I put my K's on the left and my not K's on the right, I'm going to get Kf over Kr is equal to NO2 squared over N2O4. And these two K values, then when you divide them, turn into your big K, which is your equilibrium K value, your KEQ. Right, so now this becomes our law of mass action, or equilibrium expression, or equilibrium equation that we would write, where we have our products on the top and reactants on the bottom, just because mathematically that's how it worked out. It's very simple. And then our K value is related to the fact that you had the forward divided by the reverse, right? If this was flipped, right, then our K would be the reciprocal of that. Right, because if you flip this, then we're going backwards. We're talking about the equilibrium based on the reaction happening in the reverse direction. So 1 over K would be what you get if you flip those two things. Right, so you can do it either way, but we always say products on top, reactants on the bottom, because then that K value is equal to the rate constant for the forward divided by the rate constant of the reverse. So this is your law of mass action that you can base everything else off of. So this K value can be related to a bunch of different things. One is it can be related to concentrations. It can be related to pressures, right? So in chapter 15, those are really the two things we talked about, was a KC or a KP. So in this case, we could do it either way. Since I wrote it in terms of concentrations, we can call it a KC, but we know that we could also deal with it in terms of pressures. I can do a KP and say it's equal to the pressure of NO2 squared divided by the pressure of N2O4. And we know that if we go and change that our value for our KC and KP is, whoops, I wrote it backwards. Our KP is equal to our KC times RT to the change in the number of moles that you have. So it's the number of moles final minus initial. So this would be 2 minus 1. So that would be a 1 up there. So if you took your KC value, multiplied it by RT, and then did the 1 here, that would get you your KP. Right? So this equation, I doubt they'd ever get into with you guys anymore, especially since it used to be on a periodic table, but it's not anymore. But you should understand that we could talk about this in terms of the pressures of each of the gases, or we could talk about it in terms of the concentrations of each of the gases. So what does this look like graphically then? Graphically then, what we would expect to see is the concentration with respect to time, that we would expect to see our concentration of the N2O4 dropping. And our concentration of the NO2 increasing, right? And these don't have to come together because we're dealing with concentrations. So our NO2 is going to be increasing, and we expect that to be increasing twice as fast as the N2O4 is decreasing because it's a 2-to-1 ratio, right? We might get something like that. Now, where these two lines level off is going to be dependent upon what this K value is, right? So if this K value is less than 1, it means that when we reach equilibrium, we're still going to have less than 1 would be more reactants than products. So this is what a graph would look like if your K value is less than 1, because I still have more reactants than products. When did I reach equilibrium? When the amounts of those things with time stop changing. So our equilibrium is reached somewhere around here, where you can see that your concentrations are no longer changing with time. Doesn't mean the reaction stopped. The reaction's still going on. It just means the rate at which this is being produced and the rate at which that is producing that has now equalized. So this is the situation where our K is going to be less than 1. If our K was greater than 1, then we would see something that looked like this. Right? Where our N2O4 now, at equilibrium, there's going to be less N2O4 than NO2. And if our K was equal to 1, then for the most part, they would come together and be almost identical. So that's what we're looking at when we talk about K greater than 1, means at equilibrium, more products, less reactants. If our K is less than 1, then at equilibrium, there's more reactant and less product, right? But that's when it reaches equilibrium, and that's how much is in the chamber. This isn't talking about necessarily which way the reaction's favored. What it's really just saying is when we reach equilibrium, what are we going to find in the container? Are we going to find more of the reactants still in there, or are we going to find a higher concentration of the products? That's the significance of the K value. All right, so what are some of the things we can do with this? So here we have a situation where we have a reaction where we have a certain amount of hydrogen and a certain amount of iodine in our container. And we know that we're going to eventually reach equilibrium with the hydroiodic acid, or the hydrogen iodide gas, if it is, right? So that means that we know that this is automatically going to shift right, because just having reactants is never going to just stay that way. We know that this reaction is going to occur. The question might also tell us, hey, our equilibrium constant is 51 for this, which means that I expect to have a lot more product than reactant when I'm all done. So I'm going to write my expression. 51 is equal to HI squared over H2 times I2. All right, so the question is then, what are we going to have as our amount of HI and H2 and I2 when we reach equilibrium? So what I've given you in the problem then is my initial conditions. And whenever you have an equilibrium where you know you're not at equilibrium, but you have a reaction that's going to reach equilibrium, you're always going to ice it at that point, right? You write what your initial conditions are. You write what the change is going to be. Well, the change is based on the stoichiometry. So we know that for every one of these that reacts, I'm also going to react one of those, and I'm going to make two of those. And then we say our equilibrium is going to be 1 times 10 to the minus 3 minus x, 2 times 10 to the minus 3 minus x, and then plus 2x, because we haven't figured out what that x value is yet. All right, so we go and plug that in here, and we say 51 is equal to, and we're going to plug in 2x and square that, right? Because I'm plugging the 2x in for the HI, so I have to square that. And then on the bottom, it's going to be the 1 times 10 to the minus 3 minus x, and 2 times 10 to the minus 3 minus x. Now, in this case, this would be a disaster problem because I didn't go and calculate this out. I'm actually doing it opposite the way it's in the book. So in this case, based on our equilibrium expression, x could be fairly significant. We'd have to quadratic this, but typically we can drop x out. So I'm just going to do it for the sake of saying, you know what, 99.9% of the time now, College Board is going to be like, okay, we can ignore the x. So I'm going to assume x is small, and I'm going to take it out of the bottom ones. The reason why we can do that is because if x is small, then the change in x is going to be very small compared to what the concentration was that you started with. How can you tell that? Usually it's if your K value is 100 to 1,000 times smaller, usually 1,000 times smaller is where you're sure than what your initial concentrations are. Because this happened to have a very big K value, it's going to kind of screw with all of this, right? But if we go and do this math then, I get 1 times 10 to the minus 4 is equal to 4x squared divided by 4 square root, and I get x is equal to 0.005. Okay, so the reason why I paused here is because clearly you can see that this x value doesn't work with the numbers I had there, because I would be taking out 5 times more than what I started with. So that didn't work. So I went back, did the math, put the x's back in for this case because this was a fictitious answer. And when I went back through and did the quadratic and all of that, I got my x value to be 9.36 times 10 to the negative 3, which then I can plug into here, and I can figure out what my final concentrations of all those things are. So 2 times that value then is going to be my concentration of what my HI will be at equilibrium. All right, so this got a little messy because I had a very large value for K. Most of the time when we're dealing with acids and things, our K value is a very, very small value. Remember, this does not have a unit because reaction rates, the units can be all over the place. So we just ignore this and treat it as being unitless. Just make sure that you're understanding that all these other things, in this case, were concentrations, meaning molarity. But if we were dealing with gases, those things would be pressures. So that's the way that we ice. and that's the way that we can determine concentrations of things at equilibrium based on the K value. If you can figure out what the concentrations of things are at equilibrium, then you can plug those things into the expression to find the K value. Just know that when they ask you for the equilibrium expression, they actually want you to write all of this out. So write K equals and put all the exponents in and make sure all your reactants and products are in there correctly in the right place and write it out. Okay, a lot of people take a shortcut on that and kind of skip that step or don't do a complete job and don't set it equal to K and all that stuff. Make sure you write K is equal to, and then you write all that stuff. Remember that your equilibrium expression never has anything that's a liquid or a solid in it because those concentrations don't really change. As long as you have solid left, you still have 100% of solid left, as far as what the concentration of that is. Yes, the amount might change, but it doesn't mean that you're going to change the concentration. Whatever solid's in the container is still in the container. So then the other part is related to Le Chatelier, which is shifting equilibrium. But what's also related to that is how did we know that this one was going to go to the right? Well, we knew that this one was going to go to the right because we didn't have any product, so it had to go right. The same way if the only thing I put in there was hydrogen iodide, then it would have to shift left if there was none of the other two things in there, because again, you have to have some products and reactants when you reach equilibrium. But what if you had amounts of both and you weren't sure? Well, they told us initially that our K value is 51. So if they gave us concentrations of things and we plugged it into this expression and got something different than 51, then we're not at equilibrium. And that's what we consider the Q value or the reaction quotient. So if you take the concentrations and plug them in and get a value for that, that is your Q. If Q is equal to K, you're at equilibrium. If Q is greater than K, meaning the value I get when I plug all this in is greater than 51, then that means I have too much product and I'm going to have to go back to the left. So this is going to be subtracted and those are going to be added. If Q is less than K, that means that I don't have enough product yet, so I'm going to have to keep going to the right. So this is going to be like this situation where my reactants are going to be subtracted and my product is going to be added. All right, so with all that being said, let's talk about Le Chatelier. So Le Chatelier looks at a whole bunch of different factors that we can use to change the equilibrium. So if these are all gases, we have a whole bunch of things in play. All right, the first thing that we can look at here is, well, what if we change the pressure? Changing the pressure. Well, changing the pressure is always going to shift it one way or the other based on the number of moles. Now, this is a horrible reaction for that, because if you look at this very quickly, your moles of gases are the same on both sides. Changing the pressure is not going to affect solutions. It's not going to affect solids and liquids. The only thing that changing the pressure will affect with is with gases. If one of these was a solid, let's say we're saying the iodine was a solid, well, now changing the pressure will have an impact because we have a different number of moles of gases on the two sides. If iodine's a gas, we have the same number of moles of gas, so changing the pressure does nothing. But if iodine's a solid, now we have more gas on the right than we do on the left. So how does changing the pressure affect it? Well, if I increase the pressure, what I'm doing is decreasing the volume, and I'm causing more collisions to occur. Well, which one of these is going to be affected more by more collisions? The side of the gas that has more moles. So if I increase the pressure, it's going to shift the equilibrium in the direction of the fewer moles of gas. And what that means is that I am actually going to cause our equilibrium values to change so that we can establish a new equilibrium based on the new pressures that we have. So if I increase the pressure, in this case, it's going to shift it to the left, which means that I'm going to have less product, more reactant. All right, but the pressures are still going to equalize in a way that we're still going to get the same value for K, but we're shifting it so that we're going to produce more of our reactant and less of our product if I increase the pressure. If I decrease the pressure, the opposite will occur. It will allow more of my product to form. All right. Another thing is changing the concentration or changing the amounts. Well, if I change the amount of hydrogen, let's say I increase it. If I increase the amount of hydrogen, that increases the likelihood of a collision between hydrogen and iodine. So that's going to cause the forward reaction to happen more. All right. If I increase the amount of hydroiodic acid or the hydrogen iodide as a gas, I'm going to cause it to be more likely to decompose. So what you see graphically on that change in concentration is you have like your hydrogen going down, your iodine going down, your hydrogen iodide coming up, and they reach equilibrium. So now they're all parallel to the x-axis. They're not changing anymore because your concentration is no longer changing with time. And then all of a sudden you see a spike. So that one's our hydrogen. And you see a spike in the hydrogen. So what's going to happen after that is you're going to react away more of the iodine. You're going to start to increase your amount of hydroiodic acid, and you're going to see your hydrogen decrease after that. Now, your hydrogen's never going to get back to where it was before because you added more. Your iodine now is going to be lower than it was before. Your hydrogen iodide is going to be higher. But the ratio of these three things is still going to come out to be the same value for K. So if they give you a graph and show you a spike like that, that means, hey, we just added a whole bunch of stuff to that. And the same way that we can spike it by adding more, we could also remove some. If I remove hydrogen, it's going to decrease the rate of my forward reaction because there's going to be less collisions, which is going to increase relatively the rate of my reverse reaction. Really what's happening is the reverse reaction is staying constant, but the forward reaction is decreasing, and that's what causes us to start to make more reactant when that occurs. So those are the things I could do to change the concentration. I could also change the temperature. The temperature now is going to be based on whether this reaction is endo or exothermic. So is my delta H positive or negative? So if I put my energy here, now I just made this an exothermic reaction. So changing the temperature, first of all, it's going to do two things. One is this is the only way that you can change your equilibrium constant, right? Changing everything else does not change your equilibrium constant. Changing the temperature can change your equilibrium constant. So my equilibrium constant will change value with the change in temperature. But the other thing is you have to recognize that adding energy helps the endothermic process. The endothermic process is the one that needs more energy. So if I add more energy, that helps the endothermic process. If I remove energy, that helps the exothermic process, right? Because the exothermic process doesn't need that energy anyway. Really, the reason why it helps the exothermic process is the opposite. It's not adding the ability for the exothermic process to work more. It's decreasing the endothermic process ability. So changing the temperature affects the endothermic process more. If I increase the temperature, I'm going to help the endothermic process more, which is the reverse reaction. If I decrease the temperature, I'm going to hurt the endothermic process more, which is going to cause my exothermic process to happen more frequently. So that's how changes in temperature will affect it. So in this case, since this is exothermic, raising the temperature will shift this to the left because the endothermic process will be helped more. And lowering the temperature is going to hurt my reverse reaction more, allowing my forward reaction to take control and shifting my equilibrium to the right. So the shifting is still always temporary. When we say it shifts according to Le Chatelier, what we're saying is we are temporarily making it favored in one direction until it reaches a new equilibrium. And remember, this will be new values that will end up becoming the same value for K. This one ends up being new values, which will end up being the same number for K. This one gives you new values and a different value for K. So you have to keep that in mind, that temperature is the only way to affect your equilibrium constant. So at this point, that covers everything in Chapter 15 related to equilibrium. So we're done here.